It's a different situation. Similar, but different. All right, so today we start section 4.5. Let me give you an outlook on what the rest of today and tomorrow look like, and then Monday, Tuesday. So we'll start 4.5 today. I'm not going to finish it. We'll finish it tomorrow. I'll give you a start of a 4.5 homework assignment tonight. We'll finish 4.5 tomorrow. I'll give you another homework assignment for 4.5. And then I will also give you guys your chapter review as well. I don't know if I'll give you your review sheet. I should. That means I got to make it. Okay, so I'll give you a review sheet tomorrow as well, too, just to give you guys a bunch of stuff to look through over the weekend. And then, you got nothing going on. And then after that, on Monday, we'll come back. We'll review, chapter review stuff. We'll spend some time in class reviewing it. But that's not when you do your chapter review, you know? You need to look at it ahead of time, so that way it's not just like up at the board, us conglomerating and doing problems. Have an idea of what's on there before you walk in so we can have a more meaningful review. And then on Tuesday, you guys will take your test, your 4.1 to 4.5 test, okay? And then we'll skip around a little bit after that point. But yeah, that's what we're going to do, okay? All right, section 4.5. Now, all the hard work that you've been putting in is finally going to come to fruition, okay? This unit is titled Analytical Applications of Derivatives. This is when we actually do our practical applications of derivatives. And in my opinion, this is one of the things that makes this class really cool. Is like you learn all these crazy things in math, and then this year you learn these big ideas of like derivatives and then eventually integration. But now we can see like the practical side of why it's important to learn these things and why we, what we can actually do with them in a real world situation, okay? So we spent a lot of time finding absolute mins and absolute maxes, which perfectly relates to the main focus of this section, which is optimization. If you want to optimize something, what does that mean? Just in like a real sense, if you want something to be optimized. What does that mean to you? The best, you said the most efficient, right? Someone said most efficient. So like if we want to maximize, or I just gave away the punchline of the joke. If we want to optimize profit, that means we want like the max amount of profit, for example, right? So that would be our maximum value, okay? If we have like a certain amount of material that we are using to build like a deck or a fence or something like that, then we would want to minimize that material, right? To keep our costs down, okay? But regardless, that still ties into the idea of mins and maxes, okay? So what we're going to spend our time doing is we're going to express some sort of relationship based on information that we're given and then either find the absolute max or the absolute min of that relationship, okay? Oftentimes the problems that we'll do in this section are dressed up in a bunch of different words, but underneath those words is some sort of mathematical relationship that you need to pick out and then take the derivative of and find the min or the max. Okay, just depending upon what situation that we're in. Some problems will be a little more straightforward than others. I mean, we've done a little bit of word problems with related rates already. We did some of that stuff already, okay? In this section, though, in my opinion, it's a little easier just because we'll be differentiating things in terms of one variable. We'll do some more related rate stuff in the future as well, too. But okay, so first of all, optimization. How does this look? So optimization problems are just applications which involve minimizing or maximizing something, okay? So we do that in order to find what's most efficient or the best outcome for whatever relationship we have, okay? So typically it looks like this. We have what's called a primary equation, and that's the equation that we want to either find the max of or the min of, depending upon the situation that we have, okay? And then apart from that, we have some sort of secondary equation or just information that relates our multiple variables together. So usually like whatever situation we're working with first, maybe it's like, I don't know, like volume, for example, of any given shape. Your volume of a shape usually depends upon multiple variables, right? Like if we're finding the volume of a cylinder, we would do area of the base, which is a circle times the height. So if it's a circle and we're finding the area of that, it's radius and height. So that's multiple variables, okay? What we like to do is we like to boil it down to one variable, so I can very simply just take the derivative and then evaluate after that, okay? So some sort of secondary equation or information will be given that will relate our variables together. And then we solve for that variable. We rewrite our primary equation in terms of that one variable. And then we differentiate in order to find our min or our max. Okay, a couple things that are very helpful. First of all, it's very helpful to talk about the domain in each one of these problems. That way we don't spend time hunting for a solution that falls outside of our domain. The way you could think about it, like on the quiz, is if you had an extrema value that fell outside of an interval that we were given. Like there's no point in us like trying to find what that output is because it falls outside of our interval, okay? In real world applications, usually we're not dealing with things like negative numbers very often, right? So we got to be mindful of our domain and our range in that case, all right? And then the other thing is draw a diagram. Now, it's me teaching you guys, so my drawings aren't fantastic. I think my writing on the dry erase board, like with dry erase markers, is better than the iPad. But either way, I'm not great at drawing things, so I'm gonna do my best. But always draw a diagram if the situation relates to some sort of picture, because it'll help you find your solution. Okay. All right. Let's deal with some simple stuff first. Okay, so find the dimensions of the largest possible rectangle with a perimeter of 100 feet. Now, I will say, I've never taught a group of students who is so good at doing word problems and expressing relationships with words as you guys are. You guys are really good at that. I have not taught a group of students that's this good at that. So it's really nice to have that. I mean, this is a skill that you guys practice a decent amount in HPC. So it's nice to have that for sure. So, okay. Dimensions, largest possible rectangle with a perimeter of 100 feet. Let's start with our primary equation. What are we wanting to maximize or minimize here? The area, right? So it says largest possible rectangle. So we want to maximize our area. Okay, so let's come up with an equation for our area. What is area? Yeah. Okay, so area equals length times width. Cool. All right. What other equation am I going to use in this problem? Perimeter, because they give me what perimeter is, right? Okay, so let's use that. My perimeter is 100 equals what? Very good. Okay. So if we look at the situation we have here, my area is length times width. That's the one I want to take the derivative of. I want to maximize it in this case. But it's in terms of multiple variables, right? Now I know I'm going to take my derivative and set it equal to 0. So I'm not that concerned about A, but it's the fact that there's an L and a W here that I am concerned about. I want to boil this down to one variable, okay? In order to do that, that is why I need this. Usually the secondary equation they give you is some sort of constraining value that you can then use to isolate a variable, okay? So we're going to use this expression, and we're going to solve for one of these variables. Which one do you want to solve for? Sorry, TV. L? I heard L first. We're solving for L. Doesn't matter. No. Your avenue to solve for the variable is going to be the same either way. There are some problems where it's way more beneficial to solve for height, for example, instead of radius or something like that, okay? All right, so we're solving for L. So we would have 100 minus 2W equals 2L. Divide both sides by 2. We get that 50 minus W equals L. Okay? All right, now, I feel like I have to relocate my chair. Okay, so what I'm going to do is now take that expression and then substitute it in for L into my primary equation. So that'll get everything in terms of one variable, okay? So when I do that, I would have, I should do multiple colors, A equals L, which is 50 minus W times W. So that's my new amended area formula. But let's distribute W. So we would get A equals 50W minus W squared. And now that's a good formula. And that guy is going at it. All right, so now we have our area equation. Let's take our derivative and set it equal to 0, okay? So then I'm just going to write it as A prime, capital A prime, equals 50 minus 2W. And we want to set that equal to 0. right, so when we do that, we get 50 equals 2W, which gives us W equals 25. Now, we're dealing with real world applications, so we need to make sure we put our unit of measure in there. So 25 feet. All right. Now, it says find the dimensions, so I need to find my value for L. Well, now that I know what W is, I can just plug it into my expression right next door. So then I would have 50 minus 25 equals L, which gives me a length of also 25 feet. So my area of max dimension would be 25 feet by 25 feet, giving me a max possible area of 625 feet squared. What do you notice about this rectangle? It's actually a square, right? And you'll find that oftentimes when you are optimizing shapes, they will become the paradigm of that shape. So in this case, the paradigm of a rectangle would be our square. That's like our best possible situation, okay? All right, questions there? Yay. Okay, cool. Oh, this is a good one. An open box is to be made from a 16-inch by 30-inch piece of cardboard by cutting out squares of equal size from the four corners and bending up the sides. What size should the squares be to obtain a box of largest volume? Let's underline stuff. What do you want to underline? What's important to you? You said what? That's a good place to start. 16 by 30. What else is important to you? Squares? Okay. What else is sticking out? Oh, wait. Isn't there a, this? Well, that was not the move, as the youth say. Just lower that opacity a little bit. All right, 16 by 30 squares. What else? You said what? Okay, yeah, okay. Volume is important to me. Largest, that means max, right? Okay. There's another word in here that's important.
Box.
Before box.
Obtain.
Yeah, so like open box, right? Because that's gonna become important here in a second. Okay. All right, those are the important words to me. Other stuff might stick out to you, and that's totally cool. Feel free to underline that as you see fit. Okay. All right, so I've got a 30-inch by 16-inch piece of cardboard. And then what's happening is they're cutting out squares so that they can turn up the sides. Okay? So that means I'm cutting out like squares from each corner. The question is, what should be the dimensions of that square? Like what size should that square be? Okay? So if that's the case, and that's what we're solving for, then what should I do with that square? Or should I make those values for now? Yeah, let's make them a variable to make them x, right? Because I don't know what they are. So my dimension is x at each one of these, okay? And then I don't know if you're wrapping your head around what's happening here, but what happens is I'm going to get a box. Oh, God. Don't make fun of me. Or make fun of me. I don't really care either way, but that's not that bad. Yeah, looks pretty good. Okay, so what's happening is we're cutting out like the squares of the box and then we're folding up the sides. And then it's making something that looks like that, okay? So that's what I want to find the volume of. I need to get some expressions for each one of those dimensions. So what are those dimensions going to be? What do you think? 16 minus 2x. So Rohan, you're thinking like specifically like this length right here, right? Would be 16 minus 2x. Because the length of 16, then we're taking an x from each one of those edges. And that's what happens all the way around, right? So my other dimension would be what? Very good. So we're going to say this is 30 minus 2x. We'll say this is 16 minus 2x. Now, what's the height of my box? Yeah, it's x inches tall, okay? Because when we're turning up the sides, this part that I'm cutting out is how tall it's going to be. So it's going to be a height of x. All right? Hey, what's my primary equation? Just like the very general form of my primary equation. Length times width times height, which is 3 variables. However, I have an expression for each one of those variables, right? Okay, so then let's plug in that expression, or those expressions. It doesn't really matter what order we plug it in. So let's say our length is 30 minus 2x times my width, which is 16 minus 2x, times my height, which is x. So in this case, your secondary equation wasn't really an equation. Instead, it was just information that related to our original situation that we need to use to, eliminate some variables here. Okay, I have an expression for my volume. Now I have the fun process of multiplying it out, get a better expression, taking my derivative, setting it equal to 0, and then finding my maxes and mins. First of all, though, how high can x go before it becomes a problem? What's my largest value of x that makes sense in this problem? I hear 8 and 16. Why 8? Yeah, okay, so like if you plug it into this side right here, 8's as high as you can go before you reach a value of 0, right? You do 16 minus 2 times 8, which gives you 0. And do I even want it to be 8? No, because then I wouldn't have a box, right? So my domain is going to be from 0 to 8. I should say x is an element of 0 to 8. Okay, now let's write my volume formula. Let's see if I have room to multiply it out. I don't think I do. All right, 30 times 16 is 480. Is that right? Yeah, okay. So 480. You guys are better at mental math than I am. You just are. Minus 60x minus 32x plus 4x squared. Oh, but all of that is still multiplied by x, isn't it? Okay, so then my volume formula is actually going to be, bless you, 4x cubed. And then negative 60 minus 32 is negative 92. X squared. And then plus 480x. So that's my volume formula. Okay. Now I want to take the derivative of that and set it equal to 0. So v prime equals 12x squared minus, 184, J on the money, and then plus 480 equals 0. So take my derivative, set it equal to 0. Okay? With me so far? All right. What can we get rid of? What factor out of all those? What's a common factor? Yeah, okay, 4. Yeah, 4. Sorry. Okay, so then 3x squared minus, what's it, 184 divided by 4? 46, okay. 46x plus 1, wait, what is it? 120, okay. Why was that the hardest one? All right, so then now we're hoping and praying that this is factorable. So, oh my gosh, okay. 3x, dive into quadratic formula if you want, man, go for it. I mean, we're hoping, we're gonna see. So this should be subtraction for each one. I like to start in the middle. I can't just find numbers that multiply to equal 120 but add to equal negative 46 because I have a leading coefficient. So, I don't know, I'd start in the middle, which would be 12 and 10. I can't put 12 first because then a number would be able to factor out of it. So I have to put a 10 first, 10 and 12. You guys learn guess and check, right? Use number sense and do guess and check. All right, so 3x times 12 is negative 36 minus 10. Oh, baby, negative 46. We got it right on the money. It's almost like I knew that was going to happen. Okay, so then now we want to set it equal to 0, right? So 3x minus 10 equals 0. X minus 12 equals 0. So I'd get x equals 10 thirds and x equals 12. But talk to me. Can't be 12. It's outside of the interval. See you later, 12. All right, so 10/3 is the only number I care about. Now, technically, we are finding our absolute, what is it, max, right? So we should test a slate of candidates. My candidates being 10/3, but also the endpoints of my interval, which would be 0 and 8 as well too. However, if I test 0 and 8, what happens if I test 0? 0. Do I want that? No. What happens when I test 8? We already talked about that. Okay, now we got to test 10/3. Womp womp. So we got to actually plug that into our volume formula. And you would get 4 times 10/3 cubed minus 92 times 10/3 squared plus 480 times 10/3. Let me just do some quick mental math here. What do you think? 19,600 over 27? Does that sound right? That seems right, right? I remember that number from last period. We did this example last period, of course, and I remember that number from there. 726. What'd you get, Max? 726. On the nose? No. I didn't think so. 726 point what? 726.9259. 6. Oh, okay. 726. Okay. All right. So that would be our maximum. What are we doing? Volume, right? Of our box. Okay. Now, does it ask for, it says what size should the squares be? So this, to answer the question, we would say the squares should be 10/3 by 10/3 inches, feet, horses, inches. Okay. All right, questions there? All right, what time is it? Oh my God, 7 minutes. Here we go. You ready? We can do it. I believe in us. Yeah, okay, we'll do it. Find the point on the curve y equals x squared that is closest to the point 18, 0. You did stuff like this in HPC. You did. You did, yeah. However, now you have the benefit of knowing calculus, which should make it easier. I do think you know calculus, bro. All right. Hey, I visited my friend Desmos last night, and I made a graph for you guys. There's y equals x squared, and there's the point 18, 0. So we want to find out what point is closest on the graph of y equals x squared, okay? Which means, what are we using here? We are using the distance formula. Which means, what do we need to do to the distance formula? Yeah, we need to find the minimum by taking the derivative, right? Oh, baby, that sounds like a blast. Let's do it.
You will see me tomorrow.
Hey, there's our distance formula.
Oh, wait.
We know that, right?
Yeah.
Are you telling me you don't know it? You don't have that distance formula on deck? To find the distance. We're going to use it. It's going to come up. Hey, when we did distance formula, you were typically equipped with what? What did you need to do the distance formula? Yeah, like 2 coordinate points, like values in a point, right? Now, how many coordinate points do I have? I have 1 of them, Max. But I need 2 points. Like, I got to come up with something for another set of coordinate points. No. X, Y is a great idea. But really, we should think about it like what? X squared. Because that's what y is. Y is x squared. Right? We're finding the distance between those 2 points. I don't know what point it is on here, but it's something around there-ish. That's great. Thanks, Charlie. It's something around there-ish. So that point is xy as far as I'm concerned. But we know what y is. It's x squared. Okay? Now, we need to take this point and this point and plug it into our distance formula. I'm going to make this x1, y1. I'll make this x2, y2. And we're going to have a ball. So D equals... All right, x2 minus x1 would be x minus x1, which is 18 squared, plus, see you later, Charlie. And then y2 minus y1 would be x squared minus 0 squared.
Times 2? Never mind, I know. Why are you multiplying 18 times 2?
We okay? I'm gonna square everything out.
Oh, yeah.
X squared minus 36x, and then plus 324, plus x to the 4th power. All right. Technically, I should rearrange and put that x to the 4th in the front, but we'll do that in a minute. Okay. Hey, that's my distance formula right now. Now I need to take the derivative of it. Yeah, which didn't end up being too bad. But hey, let's talk logically about what happens with this derivative. So d prime equals this, okay? We've done a good amount of derivatives involving square roots before. What am I going to use? Chain rule. So imagine it to the 1/2 power. We would do 1/2 times that same expression to the negative one. You know, I'm just going to write it out. I'm just going to do it. It's important. I'll spend my last 3 minutes doing this. All right, so 1/2 inside, which is x to the 4th plus x squared minus 36x plus 324 to the negative 1/2, and then times the derivative of the inside of that, right? So 4x cubed plus 2x minus 36. Okay, and then if I write that, it looks like this. This part goes in the bottom. Bless you. Square root of x to the 4th plus x squared minus 36x plus 324. And then let's hit a half on each one of those terms. So that stays upstairs. 2x cubed plus x minus 18. Now, what do you notice about my denominator? It's the same thing. Cody's right. It's the same thing as my original distance. So when I set this equal to 0, do I want my original distance being 0? No, I don't really care about that, right? Like, plus, is my distance going to be 0? No, because I can't have that. So for all intents and purposes, I can ignore the denominator in this case. I'm not even going to spend my time trying to solve that equal to 0. I am focused on my numerator. So 2x cubed plus x minus 18. Because again, this is the same as my distance. I don't care when that equals 0. I want to know when this equals 0. Okay? Now, unfortunately, this isn't a quadratic. It's a cubic. So I can't just factor to use quadratic formula. What do I have to do? Very good, synthetic division. So you would do it with 2. And you would find that it works out nicely. 8, 9, 18, 0. Boom. So you get x minus 2 or x equals 2 as one of your factors. Okay, this would be a quadratic then. However, the discriminant of that is less than 0. Do you guys know what that word means, discriminant? The value that's under the square root in the quadratic formula. What happens when it's less than 0? It means it's negative under a square root. Do I have any solutions? No. So that's not equal to 0. That's no solution. Okay, which means 2 is the only number I care about. Okay, so then that's what I would test. I would say that my x-coordinate is then 2. And my y-coordinate, if that's my x-coordinate for my equation, it would be 4, right? Because it's x squared. Okay, so plug it into your original, and you would get 4 as an output. That was fast at the end there, okay? All right, your homework for day 1 is listed at the end of the numbers file. Get that done.